Okay, so so any more questions before I kind of continue? I'll start. And also, midterm will include everything through this particular module. So, quick recap of what we have done before. So, we talked about a module called half adder, which takes two 1-bit numbers and adds them together to produce a sum output and a carry output. We had talked about how sum is of 2 bits is nothing but an XOR gate, and carry output in this case is then produced by the AND gate. And you can think of it as adding to 1-bit number, and so the 2 bits represent the bit in the ones position, and the sum and carry. One way of thinking about it is the sum bit and a carry out. The other way of thinking about it is when I add two 1-bit numbers, then I can get a 2-bit number in the worst case, right? Because if I add 1 plus 1, then I get 2, which is 1, 0. And therefore, I need 2 bits to represent it. And so you can think of C and S to represent that two 1-bit number. S is the ones position and C is the twos position. Okay, so you can interpret it whichever way you like. It's kind of the same thing. So half adder adds two 1-bit number to produce a 2-bit number, or another way of saying is half adder adds two 1-bit number to produce a carry, a sum and a carry. And then we also talked about a full adder, and full adder refers to a module which takes three 1-bit numbers. So when you have three 1-bit numbers, then again the output can be 2 bits, because 1 plus 1 plus 1 in the worst case adds up to 3, which means I can represent it as 1 and 1. So again, I need two bits. One of them is we call the sum bit, and the other we call as the carry out. But another way of thinking about it is that these two together represent my represents my 2-bit number. So for example, 1 plus 1 plus 1 is 3, and you see how it is 1, 1, 1 out here. Or like, for example, 0 plus 1 plus 1 is 2, which is 1, 0 in binary, so you see 1, 0 out here. So full adder takes three 1-bit numbers, produces the output. And we kind of showed that how carry out in this case can be viewed as the majority function, which we had seen before, and sum output, that's a 0th bit, can be viewed as XORing a 3-bit, XORing 3 bits. Okay, so that we had seen before. We also talked about that how I can create a multi-bit adder. So there are kind of the most common situation is I want to add two n-bit numbers, and if I'm adding two n-bit numbers, then I can in general have a carry out, or another way of saying is that I can get in the worst case n plus 1 bits, right? I mean, just like when we talk about, like, if I add two-digit numbers, then I can get a 3-digit output. So 99 plus 99 is 198. So you can, one way of thinking about it is that I get a 3-digit number. Another way of thinking about it is I'm getting 98 at the sum, and I'm getting 1 as a carry out. Same way out here. So I'm taking two n-bit numbers, and I get n plus 1 bits out here. So C out really represents that n plus 1th bit. Now in this particular case, in the lowest bit position, I'm adding 2 bits. But in every other bit position, I have to add 3 bits. I have to add the 2 bits which the inputs are providing, and I also have to add the bit, the carry in bit which is coming in. So that means in all the higher bit positions, I need a full adder, which adds three 1-bit numbers, and at the lowest bit position I need a half adder, which adds two 1-bit number. Now in certain circumstances, and which we had also gone in last time, we feel that it may be useful to control the carry in out here. So instead of assuming that the carry in to the least significant bit is always 0, maybe there are times in which I want to feed a 1 out there. Okay, so then even in the least significant position, I may need to add 3 bits. And so that there was a variant which we had where we actually use full adders all the way through. So there's a carry in out here. Now, given something like this, let's say I tell you, okay, make me a 2n-bit adder. Like, so I gave you an n-bit adder, and I want to make a 2n-bit adder. So, like, for example, I gave you 8-bit adders, and I want a 16-bit adder. What would you do? Right. So I take this module, make a copy of it, take carry out of this, feed it into carry in of the next one. Okay, so I can just keep cascading these things. We also talked about that how these kind of circuits, which we have seen many a times now, they tend to have this long chain which kind of starts in the least significant bit and kind of traverses all the way up, and so the delay of such a circuit and therefore the speed is really dictated by this long critical path that we tend to see out here. Okay, then we had made the transition to negative numbers. So thus far, we were creating all these modules, but the meaning that we were attaching to these n-bit numbers were that they were positive binary numbers. So a positive binary number basically means that the weight I give to the bit position number I is 2 to the power I. So for example, B0 has a weight of 1, B1 has a weight of 2, and Bn minus 1 has a weight of 2 to the power n minus 1. And likewise on the sum side, S0 has a weight of 1, S1 has a weight of 2, 2 to the power 1, Sn minus 1 has a weight of 2 to the power n minus 1. What is the weight of Cout? To the power n, right? Remember, we can interpret it as Cout or we can interpret it as the next bit. Okay, so that realization is always kind of something very useful. But then we wanted to go for negative numbers, and of course, if I give you n bits and I say, in these n bits you have to represent positive numbers and negative numbers, then obviously I cannot have 2 to the power n I only have 2 to the power n bit patterns. So I'm going to allocate some of them for positive, some of them for negative numbers. And there are many different ways you can do it. And intuitively, you might say, 2 to the power n choices, I'll allocate, I have to give allocate one of them for a 0. That will leave 2 to the power n minus 1 choices remaining. Roughly half of them I'll put on the positive side, roughly half on the negative side. I'm left with an odd number, so I have to make some choices. So there are 3 very common techniques which are used. And remember, as we saw earlier in the course, I can really interpret bits in whatever way I want, but not all of them make sense or abide by our intuition. There are 3 very common ones which are used. One is called sign magnitude, the other is called 1's complement, and the final one is called 2's complement, and we saw all of them as well. So the sign magnitude, the idea is that we represent the sign in the most significant bit. So the most significant bit being 0 means positive, being 1 means negative, and the remaining bits I represent the magnitude. Okay, so plus 23 becomes 10111, which is 23, and then a 0 out here, and minus 23 is the same magnitude but 1 out there. So that's convenient. Obviously, there's certain things which I can easily see what the magnitude of this number is. I can easily see what the sign is. The problem is that dealing with numbers like these, it turns out the circuits become more complicated. So it's not used that commonly. So another one is called 1's complement. And the idea in 1's complement is, but by the way, before I move on, as you can see in this case, I had 6 bits. I used one of them for the sign, so that leaves us with only 5 bits. So even though I have 6 bits, I can only go up to 31. The maximum magnitude I can have is 31. So I can represent numbers in sign magnitude. I can represent numbers from minus 31 to plus 31. And the number 0, all zeros, or 1 followed by all zeros is the same number. It's plus 0 or minus 0. It's exactly the same number. 1's complement, the way it works is the following, that for the positive numbers, again, we use the same thing, which is we put the magnitude of the number out here on the lower bits and use the uppermost bit for the sign. But for getting the negative number, what we do is we take the corresponding positive number and subtract it from all ones. Okay, and another way of thinking of that subtracting from all ones is the same as inverting each one of these bits. Okay, so you would see that plus 23 was 0, 1, 0, 1, 1, 1, and minus 23 is 1, 0, 1, 0, 0, 0, which is what we see out here. So we literally just invert each bit or complement each bit. Now, in this particular case, again, I will have 2 representations of 0. All zeros is the number 0, as well as if I take the negative of that, that would be all ones, and therefore that would also be represented by that would also be a 0. So in this particular case also, out of my 2 to the power n choices, or in this case 64 choices, I set aside 2 of them to represent 0, and the remaining I use to represent the equal number of positive and negative numbers. Now again, this is not very commonly used either, for the very so 2 reasons. Again, the circuits tend to be a bit more complicated, but more importantly, there's this ugliness that I have two patterns representing exactly the same number, 0. Okay, we just think of them as plus 0 and minus 0. So that's not good. So that gave rise to 2's complement, and of course now I will have a if we are going to have a unique representation for 0, which would be the pattern all zeros. But then that means I'm left with, in our example, out of 64 choices, 6-bit, 64 choices, I'm left with 63 choices. So clearly, I cannot have an equal number of positive and negative numbers. I'll have to have either more negative numbers or more positive numbers. So we'll make a choice out there. And the way 2's complement works is, again, positive numbers are represented exactly the same way. But for negative numbers, we first do the 1's complement, which means I flip all the bits, and then we add 1 to it. Okay, so in this case, we started out with 0, 1, 0, 1, 1, 1. We flip the bits, so we would get the 1's complement, and then we add 1 to it. So you see the 1 out here. Okay, so now thus far, these are just apparently arbitrary choices, but we'll soon see that the beauty of 2's complement is, and we kind of saw it at the end of last lecture also, that the very same circuits we were using for our positive binary numbers, so an n-bit adder designed for a positive binary number continues to be an adder for n-bit 2's complement numbers. I don't have to do anything special for that, and therefore I can take literally the same hardware and use it both for unsigned arithmetic and signed arithmetic, the same adder, and that works well. There's a certain kind of elegance to it. So let's look at the example. So this is 4-bit 2's complement number. So with 4 bits 2's complement number, I set aside 1 for the sign, and the remaining 3 are the ones which are really representing the magnitude when we are looking at positive values. So we have 0, 0, 0, 0 as the 0, 0, 0, 0, 1 is the 1, all the way through 0, 1, 1, which is the number 7. Now that leaves us with 8 choices where the upper bit is 1. So I will have 8 numbers, 8 negative numbers I can represent. So I can go from -1 through -8. And you can see that things add up. So for example, let's say I want to represent -3. So I will start with 0, 0, 1, 1. I complement it, I get 1, 1, 0, 0. And then I add 1 to it, I get 1, 1, 0, 1. And that's what you see out here. -3 is 1, 1, 0, 1. Or likewise, let's say I have 5 and I want to find out -5. So 0, 1, 0, 1, I complement it. So it becomes 1, 0, 1, 0. And then I add 1 to it. Then I get 1, 0, 1, 1. And that is what we have out here for -5. 1, 0, 1, 1 is -5. Now this thing obviously breaks down for -8 because I never had an 8. Okay. So -8 is kind of a unique thing. Now, by the way, the other interesting thing is that just like by taking 2's complement, I go from 3 to -3. If you take 2's complement of -3, you'll get back to 3, and you can test that also. So let's say I have -3, 1, 1, 0, 1. I invert it, 0, 0, 1, 0. I add 1 to it, I get 0, 0, 1, 1. So I get back 3. So if you think of this operation that we do, transformation that we do, namely 2's complement, which we define as take the invert, add 1 to it, that lets us go from a positive number to the corresponding negative number, or from a negative number to a corresponding positive number. So taking 2's complement is equivalent to saying that I am inverting the sign. I'm multiplying by -1. That's one way of thinking of it. Okay, so what will happen to -8 if I try to take its 2's complement? Well, -8 would map to 8, but we cannot represent 8. So something bad will happen. And in this case, if I take 2's complement of -8, then I will start by taking the complement. So 0, 1, 1, 1, add 1 to it, I'll get back 1, 0, 0. So -8, when I take the 2's complement, I get back -8, which is obviously a bogus result. But the reason is simply that 8 cannot be represented within 4 bits. So something bad is going to happen out here. The other thing to notice out here is that when I have 2's complement numbers, if I do arithmetic on it, so I can have bad things happen. So let's go back to our regular positive binary numbers. So if I was dealing with 4-bit positive binary numbers, then when I add them, then sometimes I needed a 5th bit. Something similar is going to happen out here. So let's say I add number 6 plus number 6. That would be 12. 12 cannot be represented in 4 bits of 2's complement. I need a 5th bit. Likewise, let's say I add -5 and -5. I'll get -10. -10 cannot be represented in 4 bits, and therefore I'll need a 5th bit. So the term which is used for this is, if I get a number which is too large, we call it overflow. And if the number that I get is too small, I get underflow. So there are these two concepts. Overflow meaning too large, and underflow is too small. So, and we'll see kind of that one has to sort of somehow be able to detect it. Now, in a regular positive binary number, if I added two numbers, so let's say I said we are doing 4-bit arithmetic, just regular positive binary numbers, and I add them, how would you detect there is an overflow? If there's a carry out equal to 1 means there is an overflow. And there can never be an underflow because we are just dealing with positive binary numbers. If I add them, there can never be an overflow in an adder. Whereas there can never be an underflow in an adder. In case of signed arithmetic, we can have overflow, but we can also have underflow. And the rules for detecting it are a little bit more tricky, and we are going to talk about that a little bit later. Now, one way of thinking about these, if I give you an n bit of information, and I say think of it as a 2's complement number, then one way of thinking about it is that the lower n minus 1 bits have a usual weight of 2 to the power I. But the uppermost bit, the n minus 1th bit, has a weight of minus 2 to the power n minus 1. Okay, and let's see if that rule works out. So firstly, if the uppermost bit was 0, then this term will disappear and I will have my regular binary representation, and therefore that will give the magnitude. Okay, so that obviously kind of makes sense. Now, if the upper bit is 1, then something bad will happen. So let's do the following. Let's pick a negative number. Let's pick 1101. Okay, so so let's say my number was 1101. According to this, the uppermost bit has a weight of minus 2 to the power 2 to the power n minus 1. N here is 4, so the uppermost bit has a weight of minus 8 as opposed to plus 8. Okay, so the uppermost bit has a weight of minus 8, so we get a minus 8 plus, let me increase the font size. Okay, so upper bit, most bit has a weight of minus 8. Next bit has a weight of 4. final next bit up has gets a 0, and the final bit gets a 1, and that adds up to -8 plus 5, which is -3. So as you can see, that adds up. Okay. So one way of thinking about 2's complement number is that the upper bit, instead of having the weight of 2 to the power n minus 1, has a weight of -2 to the power n minus 1. Okay, whereas in regular positive binary numbers, I would have it a plus out here. Okay, so this is one way of thinking about a 2's complement number. So what that also means is that if I want to represent the number minus x, then that is the same as x minus 2 to the power n minus 1, right? Because all I'm doing is I'm adding this thing up, right? In the positive number, it would have been bn minus 1 would have been 0, but now it is minus. But since whenever I'm dealing with n bits and whenever I do an addition, if I ignore the carry out, then I always do a modulo 2 to the power n arithmetic. So like for example, if I was thinking of a 4-bit binary adder, 4-bit positive binary adder, then when I add two numbers, so let's say I add 5 plus 5, 4 bits, I can go up to 15, 5 plus 5 is 10, I get 1010. Sorry, yeah, 1010. But let's say I were to add 8 plus 8. 8 plus 8 is 16, which cannot be represented in 4 bits, so I'm going to get a carry out. So I would get 1 followed by 4 zeros. If I ignore the carry out, just look at the 4 sum bits, then that is the same as 8 plus 8 modulo 16. Does anyone not know what modulo 16 means? Modulo arithmetic. Everyone knows? Okay. So, or let's take another number. 10 plus 10. 10 plus 10 is 20. 20 modulo 16 is going to be 4. So if you add 1010 plus 1010, I should get, ignoring the carry, I should get the number 4. And let's see if that indeed is what happens. So like for example, 1010 plus 1010, thinking of them just as this is just regular positive binary arithmetic, I'm going to get a 1 as a carry out, and I'm going to get starting from the right hand side, I'm going to get 0, I'm going to get 1 plus 1 0, I'm going to get a carry of 1, 1 plus 1 0, and I'm going to get a carry of 1. Okay, so this is what I would get, which if you think about it, in 5 bits it is the number 20, but if I ignore the 5th bit and just look at the sum bits 0 1 0 0, then that is 20 modulo 16. Okay, so and essentially I'm subtracting this guy. So so what that all of that leads to is the following, that I can see here I was saying that the number negative x is the same as x plus minus 2 to the power n minus 1. But what I can keep doing is that I can add to it. So let me go out here. If I have the number minus x, then the claim out here is the following, that minus x is represented as the number 2 to the power n minus x. So I take the bit pattern of x and I subtract it from 2 to the power n, and that is essentially the act of taking 2's complement. Right? 2 to the power n can be written as 1 plus 2 to the power n minus 1. 2 to the power n minus 1 minus x is the same as taking a complement. So let's write it down. So 2 to the power n minus x is the same as 1 plus 2 to the power n minus 2 to the power n minus 1 is a string of n ones, and that minus x would mean I'm going to complement x. So this part, which I have highlighted, is the same as the operation of inverting all the bits of x, and then I'm adding 1. So this is nothing but taking 2's complement. Okay, so that's how it's kind of defined out here. And what all of that translates into the following. So let's say I'm doing 4 minus 3. That is the same as 4 plus taking the 2's complement of 3. So which is what we are doing out here. And so you end up with 0, 1, 0, 0 plus 1's complement of 3, which is 1, 1, 0, 0, plus the number 1, because we really needed 2's complement. You add them up, you get the number 1 out here. And all of this magic is happening because all the arithmetic is getting done modulo to the power n. Okay, so we always kind of ignore what is happening on the carry out. So I would like you to try this thing out. I think a couple of the problems in the homework kind of make you think about it. They are pretty easy problems, but I'm just checking for whether you understood this concept or not. So there are, again, same n bits when viewed as a positive binary number. Carry, the upper bit has a weight of 2 to the power n minus 1. And exactly the same n bits when I think of them as a 2's complement number. Suddenly we change the sign for the weight attached to the uppermost bit. Okay, it's just a matter of interpretation, right? I can take any circuit and feed bits to them, and they'll produce some bits. They all have gates. The meaning we attach to the bit patterns is what gives them the meaning that we want. Okay, so if the meaning we attach to it is that, hey, they are positive binary numbers, then I will give one interpretation. If the meaning I attach to it is that they are 2's complement number, then they'll do something else. The big assertion that we are making very soon we are going to make, well, we have already made, is that when I add 2-bit patterns using our regular adder, which we already saw, if we interpret them as positive binary number, they come out right. The output is a positive binary number represented in n bits. If I interpret it as a 2's complement number, very same adder, the one which we saw a few slides ago, continues to add as an adder, except that this time around for the 2's complement number. So it takes 2's complement numbers in, produces 2's complement number at the output. The carry out would still work, except that carry out will no longer mean necessarily overflow or underflow. So we'll have to look into that a little bit carefully. But the adder behaves as an adder. So so that's nice. The other thing we talked about last time was that, okay, what if I want to subtract two numbers? So I want to do a minus b. Now we never studied how to subtract two positive binary numbers. Okay, we never saw that if a and b are two positive numbers, I do an a minus b. Well, part of the problem is that if I gave you two positive numbers and I said do a minus b, if b was greater than the a, then we'll end up with a negative number, and we don't know how to even represent it, right? So if we are talking only about positive binary numbers, subtraction is a little bit dicey. But when we are doing 2's complement numbers, subtraction is fair game. So then what it boils down to is, and let me again kind of write down out here. So say I want to do a minus b. This is the same as a plus minus b. So I'm continuing the example previously shown, which is the same as a plus 2's complement of b, which is the same as a plus invert b plus 1. Okay, all I'm doing is I'm just replacing, saying that, look, taking the negation of b is the same as a minus b is the same as adding negated b to a. Negation of a number is the same as taking 2's complement, and 2's complement is the same as inverting the bits of B and then adding 1 to them. And so now all that's happening is that A minus B for 2's complement arithmetic is the same as interpret A as a positive number, interpret and interpret B as a just a positive bit string, but now we take the invert of that and do 1, and that's what we are representing up out here. I am feeding A to my adder as is, I'm taking B, and then I'm complementing it if I want to do a subtraction. So this module out here, if sub is 1, okay, so this is a funny kind of a module which basically seeks to, if the line sub is 1, I want to do subtraction, that is I want to do A minus B. If sub is 0, I want to do addition, I want to do A plus B. So now if you see if sub is 1, then what will happen is I will have a carry in of 1, and the XOR would have 1 feeding into it, and some X XOR 1 is the same as invert X. So what we'll see out here is invert B, and therefore it will act as this guy. If on the other hand sub is 0, then carry in is 0, and B XOR 0 is going to be B, so this guy will just do A plus B. Now, moreover, A and B could themselves be, since they are just 2's complement numbers, so they could themselves be negative numbers also, either one of them or both of them. So like for example, A could be minus 3, B could be minus 5, in which case I'll do minus 3 minus 5, which is the same as minus 3 plus 5, which should give us the result 2.
How does B XOR 1 work for like multi-bit?
Yeah, so this is kind of a weird thing I've done. Think of this gate as there are n XOR gates. The second input of all of them is tied to sub, whereas the first input of each XOR gate is tied to one of the bits of B. Okay, it's just stylized drawing. Okay. Any question on this? So the deep thing going on out here, because I'm jumping back and forth between same A and B, at times thinking of them as 2's complement numbers, and then at other times as thinking of them as just a binary vector. Okay, a bunch of bits. Okay, and you're kind of going back and forth between them, and that's very important. That remember, this adder that we had originally designed is a very same adder which we saw some slides ago. Bunch of full adders with a carry in and a carry out. There we were using it for just adding 2 n-bit numbers, but now suddenly I'm using it to add and subtract signed numbers, and things just magically kind of work out. So it actually is the very same design. I mean, this guy is just replaced out here. Now let's talk about overflow and underflow. Okay, so we are going to call both of them overflow. So overflow means my number is either too positive or too negative, that is larger than the largest positive number and smaller than the smallest negative number. Okay, and this can happen whether I'm doing addition or subtraction. So like for example, if I added, let's say we are talking about 4-bit 2's complement numbers, and I added 7 plus 7, I'll get an overflow, right? Because 7 plus 7 is 14. 14 is not representable, so I should get an overflow. On the other hand, if I added minus 7 plus minus 7, I'll get the number minus 14, which also by our logic results in an overflow or underflow more precisely. Can subtraction result in overflow? Give me an example. Okay, so if A is positive, B is negative, so like 7 minus 7 results in overflow. So both positive number, addition and subtraction can both result in overflow and underflow, which we collectively call as overflow. So now let's think about how we can detect this overflow business. Okay, so let's first talk about the number becoming too positive. Okay, so when can a number become too positive? Well, there are two scenarios. I'm adding two positive numbers, or alternatively, I'm subtracting a negative number from a positive number, right? So 7 plus 7 or 7 plus 7 minus 7, right? So these are the two scenarios. In the first scenario, so let's say that's what you are doing, 7 plus 7, then XOR will not have any effect because we are not doing 2's complement. So I will just get 7 plus 7 out here. If on the other hand, I was doing 7 minus 7, then that would be the same as taking the 7 plus 2's complement of minus 7, which is the same as 7. So I'll end up with 7 plus 7. Okay, so again, my adder will see 7 plus 7. Now, with the 4-bit 2's complement, I can, since if I'm looking at positive side of things, the upper bits are always going to be 0. So A3 and B3 are always going to be 0. So this thing is going to be 0. My 1, 1, 1 are residing in the lower 3 bits, the lower n minus 1 bits. So the carry out, if I have a number which is too positive, then there will be a carry out of this bit. Like there will be a carry in going into the most significant bit. But out of my most significant bit, the carry out will be always 0. Okay, so let me so let's consider the case that I'm looking at n equal to 4, and I'm considering a equal to 7, b equal to 7, and I want to do a plus b. Well, that is the same as saying 0, 1, 1, 1 plus 0, 1, 1, 1, right? And if I add these things, then I'm going to get the number 14, which is, if I were to think of these things as just a positive numbers, then I'll get the number 14, which is 1, 1, 1, 0, right? So that will give us 1, 1, 1, 0, and you can check that's what happened. 1 plus 1, 0, 1, 1, 1. That's what we are going to get. The problem is that this 14, if I'm interpreting everything as 2's complement, this is a negative number. What negative number is this? Anyone? Negative 2, right? Okay. So clearly, and you can see that negative 2 modulo 16 is 14. Okay, we just add 16 to it. So now the problem is that, so obviously something bad happened. I took two positive numbers, I was adding them, and I ended up with a negative number. So it's obviously not possible because I should get a positive number. So looking at this, and this is the worst case. Looking at this, what you see out here is that there was a carry out which was going from my 3rd bit to the 4th bit. That carry out was 1. So carry out from, or rather, bit 2 to 3. So let's call it C out. How are we labeling things? Okay, so we are calling C out from 2 to 3 is 1. And what is the overall C out? That is 0, because when I add even the most positive number, 0, 1, 1 plus 0, 1, 1, I would never exceed the number 15, right? 1, 1, 1, 1. I'll never exceed that. So this is 0. So looking at this, what stands to reason is that if I take my lower n minus 1 bits and I think of it as one adder, and I just think of a separate adder, 1-bit adder for the most significant bit, then whenever I have an overflow as in too large a positive number, then the carry which is going into the most significant bit is going to be 1, and the carry which is coming out of the most significant bit is going to be 0. Okay, now let's think of the most negative situation. So what's the most negative number I can represent?
Negative infinity.
No, I can't. Your score will be negative infinity with that, unfortunately. But okay, so if n was 4, what's the most negative number I can represent? -8. And therefore, my worst case situation is going to be -8 plus -8, right? Because then I will end up in -16, which is not possible to represent. Um, or another situation might be that I do -8. So one situation is -8 plus -8. The other situation is -8 minus 8. Okay, so I'm doing a subtraction. Both of them will result in the same pattern out here. But if you see, what will happen is I'll be trying to add 1 followed by, so the MSP is going to see 1 coming in, and all the lower bits are 0. So the carry in coming into MSP will be 0, and carry out coming out of the MSP would be 1. It's exactly the opposite situation. So what's happening is, in case of too positive or too large a positive, carry of 1 into MSP, 0 out of MSP, and too small or negative. Okay, by small I mean more negative than the most negative number. Then I'm going to see carry of 0 into MSB, 1 out of MSB. And all other situations where the carry coming in into the MSB is 0 and out of it is also 0, or it's coming in as 1 and out of it is 1, they are just normal situations. And therefore, that gives me the rule on how we can detect overflows when I'm doing 2's complement, when I'm interpreting the inputs as 2's complement. I have to look that the carry into the MSB and the carry out of the MSB are different, which is why I have this XOR gate. XOR gate checks for the 2 bits being different. So kind of our beautiful kind of n-bit structure has a little bit of ugliness. Now we cannot just look at the carry out of MSB. I also have to look the carry getting into the MSB, and I have to XOR them, and that is what gives me overflow. And this overflow tells me both whether it is too large positive or too small negative, that is more negative than what I can represent. So our good old adder, with this slight modification, also tells us that there is an overflow happening, or overflow or underflow, too positive or too negative. Now, just let's talk a little bit about it. What should happen? So let's say you're writing a program. Your integers in your Java or C++ programs are usually 32-bit. In some computers, they're 64-bit. Let's say you add 2 numbers which are, by the way, almost every computer I know of is 2's complement arithmetic. Okay, so you can try write whatever language you're familiar with, C++ or Java. Just do the following: like declare 2 int variables, make them to be the largest int variables, add them, and store them back into an int. You would see you'll get a negative number. Okay, of course, which doesn't make sense, but that's what will happen. What should happen if you were designing something? What would you like to do if I add 2 numbers which are too large? They're both positive, but they're too large to be represented. So right now what happens is we get a negative number. Okay, and of course this overflow bit will get set, but there is no way we really get to see it in our program. So can you think of some alternative design philosophy that you might like to follow? I'm adding 2 numbers at 2 positive. What would you like to see happen? Huh? Okay, so one possibility is error. So one possibility is overflow suddenly causes your program to crash, saying, "Hey, overflow happened." Okay, and then you can, or somehow some sort of signal coming to your program saying something bad happened, event of some form. Okay, most operating systems provide that. So that's one possibility. Can you think of some other alternative?
If we're okay with modular decomposition, like if we're working with a clock or something like that, we could just ignore it.
Okay, in some applications could be ignorable, although if that's the case, you should probably not be using int, you should probably be using unsigned int. Okay, so not generally kind of a good policy to follow. What else could you do?
Modulo 2 and -1 to like bring it back to positive.
But you don't even know it happened, right? So unfortunately, you can't. What else? So there's another concept which is often. Oh, go ahead.
It says that it's a 0. It's positive and positive is never going to be 0. So it just like as an error code.
Well, then how do you know that it wasn't really 0 to begin with? Yeah. Now, there are various ways to kind of handle this thing. One is in some programming languages, they provide something called big int, okay, which basically use some internal arrays or vectors to kind of represent arbitrarily large number. Like for example, Python has a big int package, okay, Python programming language, and most programming languages have something like this. Okay, so let you deal with arbitrary large numbers. So they are no longer packing into a single n-bit number. That's one. Another possibility in many applications, you can say, you know, if the number becomes too positive, just saturate it. So like the idea would be +7 instead of being 14 would remain +7 because that's the highest positive number I can represent. So it's called saturating arithmetic. Okay, that's the term which is used. So one could have this concept of saturating arithmetic also exists. Okay, so what it does is if the resulting value is too large, I'll cap it. If it's too small, I'll cap it below. Okay, so -5 plus 5 instead of giving us 10 is going to give us 7. Okay, and in many cases it's fine. Like when you are dealing with physical world signals and all, you kind of essentially like chopping the signal off. But in other applications, it could be a huge problem. So somewhat application specific. Okay, reverting back to our story out here. So same adder, like the same binary adder that we have been dealing with this minor enhancement lets us do overflow. And then as we talked about, perhaps this overflow can be made visible to rest of your system, to your software, so that if an overflow happens, you can go and make some corrective action based upon that. That's kind of the idea. So now that we have 2's complement, we can add 2's complement number, we can subtract 2's complement numbers, we can detect overflow / underflow, then we can start doing other kind of interesting stuff also. So for example, if I want to say make a comparator. Now remember, previously we made a comparator where a greater than b, you recall from the previous module, but that was for 2 positive binary numbers. And we had designed a circuit where we were passing information, we were matching bits by bit, and then we were doing stuff. But once we have a subtractor, I can make a comparison very easy. So let's say I want to compare A and B. Then I subdo A minus B. If the result is positive, then I'm in okay shape. If the result, then that means A greater than B. If the result is negative, then also it helps us because that tells us that B is greater than A. Of course, the gotcha out here is that I may have overflow or underflow happening, so you have to detect it. So the idea is the following. So one way you can say is the following. One rule you can follow is the following way. So you can say, if no overflow happened and my result has a MSB of 0, then that means A is greater than B. If no overflow happened and MSB is 1, then the result is negative and therefore B is greater than A. If an overflow did happen then you have to do some additional work, and I'll let you think about what additional work you have to do for that. Okay, so but you do have to worry about that situation also, because remember, now we are dealing with kind of signed stuff. Okay, now what you could also do is that I can just introduce an extra bit. So what I mean by that is, let's say you are dealing with n-bit signed numbers, n-bit 2's complement numbers, and you do not want to worry about overflow and underflow. You always want an output which you can think about regularly. So one cheating way is the following. Instead of thinking of n-bit numbers, use n plus 1 bits. And then do the subtraction or addition, as the case may be. So let's think about it. So let's say I had let's say I was dealing with 4-bit 2's complement numbers. So I would represent the number 7 by 0, 1, 1, 1. And the problem with this is that when I added 7 plus 7, I'm going to end up with 14, which is not representable. What I'm suggesting is that instead of using it as 4-bit, let's make it 5-bit artificially. Because once I have 5 bits, overflow will never happen. Okay, and so 0, 1, 1, 1 will become 0, 0, 1, 1, 1 in 5 bits. And now when I add this thing, even after addition, my result will still fit into this thing. I'll never have an overflow. Let's talk about minus 7. So what is minus 7? Anyone remind me? 1, 0, 0, 1. Okay. What would be its 5-bit representation? So if I said instead of using 4 bits, use 5 bits. 1, 1, 0, 0, 1. What happened? See, the signed bit just got repeated out here. Okay, so this is called sign extension. The sign extension, basically what it does is it retains whatever the value the number had, but it's just representing it at higher and higher number of bits. So positive numbers, we just put zeros in the front. Negative numbers, we just put ones in the front. The rest of the stuff remains the same. So if I want to compare, if I'm worried about overflow, underflow, I can always kind of cheat and add an extra bit, or alternatively deal with my overflows and kind of work things out. But anyway, the message I want to give out here was that once I give you a subtractor, once you know you have a subtractor, then you can always make a comparator out of it. And as to if I only gave you an adder, then we already showed that you can, by using those XOR gates, you can make a subtractor out of it also. And in fact, you can make a module which does both addition and subtraction. In Logisim, they have a addition module and they have a subtraction module also. Okay, but if you want to do the same operation, you want to do both the operations in the same module, instead of using a separate adder and a separate subtractor, it's going to be a lot cheaper to use an adder plus the XOR gates. Okay, let's see what else. Let's say I want to multiply a number by 2. Okay, I want to double the number. So and if I don't give you a multiplier, what would you do? Just add yourself. And what does that translate into? So let's look at 0, 1, 1, 1 plus 0, 1, 1, 1. What would happen to that? Shift left. So you put in a, shift all the bits and put in a 0. Okay, so now let's say I ask you, let me So what we are trying to do is to multiply by 2. So 0, 1, 1, 1 times 2 is the same as 0, 1, 1, 1 plus 0, 1, 1, 1 equals to, it's the number 14, so it would be 1, 1, 1, 0, okay, which is the same as left shift by 2. Okay, let's say I were to ask you, design me a module which left shifts a number by 2.
So left shift by 2 or
Sorry, left shift by 1. Apologies. Okay, left shift by 1. So let's say I were to ask you, I have a design a module which is taking a 4-bit number and left shifts the number by 2. So output is equal to input left shifted by 2. How many gates will you need? Huh?
8 gates, right?
How many gates?
8.
8 gates. Okay, so we are talking about 8-bit numbers. Is that what you mean?
No, 4-bit number.
4-bit number. Yeah. So
Each
how many?
letter have 2 gates.
Okay, so you think each number will have 2 gates. All I want to do is left it by 1. Okay, so 8 gates is this answer. Anyone can do better?
0 gates.
0 gates. It's just wiring, right? I take bit number input 3 I ignore, input 2 I feed to output 3, input 1 I feed to output 2, input 0 I feed to output 1, and tie output 0 to a 0. So if I'm shifting by a constant amount, it's just a wiring game, no gates. It's only when I asked you to design a module which has to shift a variable amount of thing, right? Sometimes I give you some sort of a control signal and say, depending upon that control signal, shift by 1 or 2 or 3, left or right, then you start needing gates. But if all I say is design a module with shift by k, which left or right, which k is constant, then it's just wiring. Question.
Would you have to have a gate to do sign extenders?
Not even not even that, because all it means is that you just repeat the same wire. Okay, so let's come to that. Okay, so you jumped ahead a little bit, but because we're talking about left shift, but let's talk about right. Before we go to that, this thing also works for negative numbers. So let's verify that also. So let's take the number -4, -3. So what is -3 in 4 bits? 1101. Okay, so I want to do -3 times 2, which would be -6, which can fit into 4 bits, so that should work. So now I want to do 1101 times 2, and now what we do is we apply our left shift game. So it would become 1010, right? 1101, 1010, good. And what is this number? Well, we take its 2's complement. So that would be 0, 1, 0, 1 plus 1, 0, 1, 1, 0, which is 6. So this is the same as -6, which works out fine. So my left shift stuff worked out perfectly fine for as long as there was no overflow happening in this situation. Now, to divide a number by 2, same story, except in the other direction. So now with division, there's always a problem, because if I'm dividing by 2 and if the number is even, we are okay. But if the number is odd, then I have to ignore the remainder. We are not going to have the remainder. Okay, so let's do 0, 1, 1, 1. 0, 1, 1, 1, which is number 7. Divide by 2. Unfortunately, I don't have a division symbol. So the claim is that this is the same as 0, 1, 1, 1, right shift by 1. Except what we are going to do is, on the sign bit, I'm going to feed the sign bit itself. So I'm going to keep repeating the sign bits. So in this case, it's 0. So that would translate into 0, 0, 1, 1, which is a number 3. 7 divided by 2 is 3 if you ignore the remainder. Okay, so that works out fine. Let's look at negative number. So let's take negative 7. So what is negative 7? 1, 0, 0, 1 divided by 2, same as 1, 0, 0, 1, right shift 1, which is the same as, and now since the upper bit is 1, so we are going to repeat the sign bit. So it would be 1, 1, 0, 0. Okay, so the rightmost one falls off, everything else shifts, and I re-inject the sign bit out here. Okay, and this one is 1, 1, 0, 0. If to find out its magnitude, it's obviously negative. Find out its magnitude, it's 0, 0, 1, 1 plus 1, which is 0, 1, 0, 0, which is 4. So this is really minus 4. Okay, and what is happening out here is we had started out with minus 7. Minus 7 divided by 2 is minus 3.5. What it is doing is it's actually taking us to the next whatever, the highest integer, just smaller than my answer. Okay, so minus 4 is just smaller than minus 3.5. Okay, it when it comes to rounding in computers, for positive numbers, it always goes towards 0. It truncates. For negative numbers, it depends. Some computers truncate towards 0. Some computers truncate towards minus infinity. In this case, it's truncating towards minus infinity. So minus 3.5 becomes minus 4 as opposed to becoming minus 3. So multiply and divide are really operations of shifting, except shift, and they also work with our 2's complement stuff also. If I want you to, if I tell you divide by, multiply by 4, what would you do? Anyone from back of the room? Multiply by 4. Shifted by 2. Divide by 4. Shift another direction by 2. Okay, now let's take it a little bit step further. I want to say multiply by 3. How will you do?
Multiply by 2 and then add 1 copy of it.
Copy. Okay, so I can think of 3 as multiply by 2 and multiply by 1 and add the 2 together. Multiply by 5. Multiply by 4 and then add the thing together. Multiply by 7. How would you do that? Okay, and how would you multiply by 6? Because we have to break it into power of 2. So multiply by 4, multiply by 2, multiply by 1, add the 3 numbers together. Any multiplier can be broken up as a sum of powers of 2. Any number can be broken up into a sum of powers of 2. That's the binary representation, right? So all I have to do is to kind of generate each one of those things via shifts and then add them together. So addition and shift together gives us multiplication, gives us division. We have sort of that's kind of the underlying theme. Okay, so now let's go through the slides. So multiplication. So shifting left multiplies by 2. We kind of already saw examples. So 5 is 1001. The 10, the number decimal number 10 is 1010, which is left shift by 1. The number 20 is multiplying that by 2, which is 10100. So that thesis holds. Multiply by 3. 3x is the same as x plus 2x. So any constant multiplier, I can always break that constant into a bunch of powers of 2 and then do each one of them separately and then add them together. So 7 times 5, if I want to do, so one way of thinking about this is the way we do long multiplication. So in our decimal thing. So let's say we want to do 111 times 101. The first thing we do is we multiply the multiplicand, which is the top number, by the least significant digit or bit. So 111 times 1 is the same as 111. So we just repeat that. 111 times 0. Now 0 is in the 2's position, or in our decimal case it would be the hundredths position, it would be the tens position. So it's shifted left by 1 because it has a power of 2. So this is what it would look like, 0, 0, 0. And then finally we want to multiply by this one out here, but this one has a weight of 4. So it's really 111 times this one is really multiplying 111 by 4, which is left shift by 2. So this is what we get. And much like our regular decimal addition, these things which we fill with 0, we add them together, we get this number 100011. Okay. If I multiply two n-bit numbers, positive numbers, how many bits would I need in the worst case to represent the output? So two 3-bit numbers, how many bits in the worst case? Well, you can see out here, I need 6, okay, at least. Do you think we may ever need 7? Well, you can work it out. Highest 3-bit number is 7. 7 times 7 is 49, which can be represented in 6 bits. Okay. So 3 plus 3, 6. Okay. What if I gave you an n-bit number and an m-bit number? How many bits would I need for the product? N plus m. Okay. Again, you can take the analogy from your decimal arithmetic. So I always need, if I give you two numbers and I multiply them together, the number of bits I need in the worst case is the sum total of their bits. Okay, so in this example we saw that, and the reason is, remember, I'm kind of shifting these things out here, and I can also have a carry out, which is kind of giving me this. So how can I now make a multiplier? So well, let's look about it. So these things, much like our what's the when we are taught multiplication in elementary school, what is a term given to these things? Each one of these rows. Partial products. Okay. I don't know, maybe it had some other names also, but I learned it as partial products. So what we really have is a bunch of partial products, and they're shifted. Now the nice thing out here is, unlike our decimal one, I'm only multiplying by 1 or 0. So all I need to do is to either repeat it or put a 0 out here. So that's nice. So multiplication by 1, multiplying any number by 1, what logic gate does that correspond to? Huh? Okay, let's do it. Huh?
Just a wire?
No. It's an AND gate, right? So 1 times 1 is 1, 1 times 0 is 0, 0 times 0 is 0, and I guess 0 times 1 is 0. Okay, so it's 1 only when both bits are 1. Okay, so multiplication by 1 is nothing but an AND operator. So as you can imagine, that I will have a bunch of AND gates. One of their bits would come from the multiplier, and the other, so if I'm looking at the first partial product, I'll have 4 AND gates because I'm looking at 4 bits in this example. One input of each AND gate will be tied to the lowest bit of my multiplier, and the other bits are going to come from the different bits of my multiplicand. And that will give me the partial product. If the multiplier bit is 0, then I'm going to get all zeros. If the multiplier bit is 1, then whatever is a multiplicand will appear out here. And I repeat the same game for all the other partial products, but I just keep shifting left by 1. Because that's what we do, right? I mean, every time we form a new partial product, I kind of keep shifting them left by 1, which is really kind of just a matter of wiring. I mean, the way of drawing things out. So this partial product is drawn so that its least significant bit is actually in the 2's position. The third partial product, its least significant bit is in the 4th position, and so on and so forth. And now I just need to add them together. That's how we do multiplications. So this is where kind of things begin to get a little bit more interesting. So if you think about it, let's look at the rightmost column. What is its weight? It's in the ones position. So its weight is 1. If I look at the second column, it's in the twos position. Its weight is 2. If I look at the third column, its weight is 4, and so on and so forth. Now let's talk about, if I look at, if there were to be any carry out of a column to the next column. So let's say I'm looking at the ith column and it has a carry out. What is the weight of that carry out? What's the weight of the ith column? I equal to 0 onwards. It's 2 to the power I. What's the weight of the carry out? 2 to the power I plus 2 to the power I plus 1. Okay. So if you think of each bit as having a weight, then the thing to bear in mind is I can only add bits which have the same weight. Okay, that's a very important thing. Remember, once I'm throwing many bits at you, in this case, we have all these bits floating around, I can only add bits which have the same weight. It doesn't make sense for me to, if I'm adding, like, let's say I gave you 10 decimal numbers and I told you to add them together, you can only add the units digit together and then take their carry out and then feed them to the tens and so on and so forth. You cannot take the digit at ones place in a number and add it to the digit which is in the hundreds place in a different number. I cannot mix weights. I can always only add things which have the same weight. So it's a similar concept that we will have to use out here to pull things together. So in any case, right now what we have is I have a bunch of partial products and I'm going to add them together. Well, if I look at the lowest one, that's simple because there is only one bit out here. So this one bit can just flow down. If I look at the second column, I have 2 bits which I need to add. And in the worst case, they can give a carry out. Right? And that carry out will feed into the next column. And likewise, now in the next column, I can have up to 4 bits to add. Right? There would be a carry out from the second column into this column, and I already have 3 bits. How can you add 4 bits together? How can we add 3 bits together? With a full adder. So 3 bits get added with a full adder. How can I add 4 bits together? Huh?
Another half adder.
Connect the half adder where?
The C out of the.
So let's try to draw it because I didn't have my stylus today. So I'm going to try it here. So let's say, so I have 4 bits and they obviously have to, okay, I'm a little bit worried about the audio, so let me do the following. Okay. So let's try it here. Okay. So what I want to do is I want to design a module which takes 4 bits and adds them together. Okay. Now, firstly, how many bits of output would I need? Okay, so what's the largest number that can be formed if I add 4 1-bit numbers? 4. How many bits do I need for it? 3. Okay, so I'll need 3 bits. Now, all of these guys have a weight of 1. 2 or 0 or 0 or 0. I need 3 bits out here. The weight of 2 or 0, so 1. Right? So that would be the worst case situation. Now, let's try adding them together. So remember, half adder, full adders, and addition is associative as addition is commutative. All those properties kind of hold true. So let's call these bits to be D, C, B, and A. So what I'm going to do is I'm going to take A, I'm going to take B. And let's stick with one solution first. A, B, and C. I'm going to take all of them together into a full adder. Remember, a full adder takes 3 bits, carry in and 2 bits, and it produces 2 outputs. So it's going to produce 2 outputs. One of them is going to have a weight of 2 to the power 0. The other is going to have a weight of 2 to the power 1. That's the carry out. This is sum. And this is in2, in1, and this is carry in. Okay, so I'm using this full adder in this way where I feed the 3 bits at 3 of the bits, and then I get 2 bits of output. I still have one more bit remaining, B, whose weight is also 2 to the power 0. So I have to add it to this bit. So I'm going to feed this to a half adder, because half adder adds 2 bits. So I'll have D out here. And output of this is going to be 2 bits. One of them will have the weight of 2 to the power 0, the other will have a weight of 2 to the power 1. So at this stage, I have 1 bit with 2 to the power 0, and I have 2 bits with weight of 2 to the power 1. Well, I need to add them together. I use another half adder. Now remember, here I'm adding 2 bits of weight to the power 1. So my sum will have a weight of 2 to the power 1, carry will have a weight of 2 to the power 2. And this, and this together form my 3 bits of output. So can anyone suggest me a different way of doing things? Let's say I did not have a full adder. Okay. So now I want someone to try. So remember, here I took a full adder. Let's say I were to say use only half adders. Want to draw?
Sure. So I guess if you can make a full adder from 2 half adders.
Just think in terms of half adders.
Okay.
Just draw it with half.
So
You might want to just come to the side so that everyone can see.
So this will give you 2 to the power 0. And then this will go.
It's messy, yeah.
Great.
Okay, so you ended up with 4 outputs. What happened?
What?
You ended up 2 to the 0, 2 to the power 1, 2 to the power 2.
This is 2 to the. No. Oh, okay. So 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0.
You got 4
What did I
bits.
do?
So what happened? Anyone?
Your D should be connected at the very end, yes, instead of early on.
Okay, why don't you come over? Huh?
Just giving a suggestion.
Yeah, it's worth a try. Okay. Come on.
We have time.
Midterm is coming close. Yeah, we have plenty of time. Well, so in your circuit, what would happen is that final bit will always be 0.
Okay.
Okay. Uh,
You want me to draw?
yeah, draw here so that. No, that's not to the power 0. It's going to the power 1 and to the power 2, right? Because you are already, the fact that these have weights of 2 to the power 1, that means you are shifted to the left already,
Right.
right? So now when you do a half adder, you will end up with 2 to the power 1 and 2 to the power 2.
Oh. Well, I didn't mean to do that then. Is that? I think I'm just wasting time here.
Yeah,
I can figure
you
it
are.
out later. Yeah.
Okay, good. Which was nevertheless useful. So anyway, I would like you guys to think about it, right? But the main concept I want to take away is when you have a bunch of numbers being added together, you have to be very conscious of whether they have been shifted or not. And you can only add things which are at the right alignment. Okay, I cannot add two partial products randomly. They are shifted by a particular amount. Another way of approaching this problem, by the way, would have been to add A and B and add C and D. And then you will have, so let's try that and see what that leads to. So I take AB, feed them to a half adder. I get two outputs. I take CD, feed them to the output. I get so weight of 0, weight of 1, weight of 0. I take these two, add them together, power 0 to the power 1, add these together, get to the power 1 to the power 2, right? To the power 1, yeah. I take this guy, add them together, 1 or 2, and then I'll back to the same thing. Okay. The only thing is, so whichever way we are doing, once we are using these half adders, we're ending up with 4 bits, but you'll have to just reason about it and you'll convince yourself that 4th bit will always come out to be 0. Okay. Even so that fact that we are getting 4 bits is kind of a fictitious thing out here. So one has to be a little bit careful when approaching these things. But the key thing going in, we know, is that if I'm adding 4 one-bit numbers, I can never have more than 3 bits, right? So just from that assertion, I mean, there should not be that 4th bit out there. Another way of saying it will always be 0. Okay, so back to our problem. I have a bunch of these partial products. I have to add them up. In some columns, I may have a whole bunch of ones. So let's look at so first column, no carry out. Second column, there is some, but a carry out possibility. Third column, I have 4 bits, and that basically means that I am getting 2 bits of carry out, right? Because 4 bits can add up to a 3-bit number, which means that this guy is feeding a carry to the next column and also to the column after that, right? And then in the next column, I have 4 original numbers plus a carry coming in. I have 5 numbers, 5 bits. How many bits do I need? 5. How many bits can 5 in 1-bit number add up to? Oh, sorry. Okay, so let me repeat it. So first column has 1 bit, so it will produce 1 bit out here, no carry out. Next column already has 2 bits and no carry in coming in, so it will produce 1 bit out here, but since 2 1-bit number can add to 2 bits, it will produce a carry going into the third column. So third column has a carry coming in and 3 innate bits, so I have a total of 4 bits. And we just saw that 4 bits can yield a 3-bit number, right? And one way of thinking about it is that the 2 upper bits constitute carries to the next two columns. So if I look at the fourth column has a carry bit coming in, and it already has 4 bits out here. So it's 4 bits plus carry, total of 5 bits. How many bits would it produce? The number 5, I need 3 bits. So this guy is also going to feed carry for the next two columns. So if I look at the next column, it has 3 bits originally. It got a carry from each one of the 2 previous bits. So it too has 5 bits out here. And you kind of flow that computation in. So this problem really is one of adding a whole bunch of ones, except that the weights of these ones are different. And so you have to keep track of the weights as you're kind of adding them, which is essentially what division boils down to. So we see how it is going. Oh, go ahead.
For the previous one, how does A2 carry into A4 again? Or
How did what?
you said that it carries into the next two columns?
Right. So if I look at let's say this column, the third column, which my cursor is moving above, it has 3 inputs which are coming from the partial products, and it will also get a carry coming in from the previous column. So I have 4 1-bit numbers, and we saw that 4 1-bit numbers can yield a 3-bit output. Right? The lowest bit has the same weight as this column, so that stays out here. But the next 2 bits have the weights of these 2 next columns. So one of the second bit will feed into this column, the fourth column, and the uppermost bit has a weight of the 5th column. So you have to put the outputs coming out of each thing into the right place, okay? Because they represent different weights, and that's important to keep track of. You can only add bits which have the same weight. Just keep that in mind. So the next diagram kind of makes it a little bit clearer. So let's try that. So again, first column feeds as is. Next column, I have 2 bits to add. So what I do is I use a full adder and put a carry in of 0, or I could have used a half adder. The sum bit of full adder comes out in the product, but its carry has a higher weight. So the carry has the same weight, this thing has the same weight as the next column. So in the next column, I really have 3 bits plus the carry coming in. I have 4 bits to add. So what I do is I use a full adder to add these 2 bits and the carry coming in. This produces a product, this produces a sum which has the same weight and a carry which feeds to the next guy. And when I add this one with the existing remaining bit, again I have the same thing, which is I get the product and I get a carry in. So if you see the next column, it really has 2 carry in coming in. That's one way of thinking about it. Another way is that if I'd already added them, then there would be a carry feeding in out here. So there are 2 carry in coming in from the previous column. So in this column, I have 1, 2, 3, 4 original bits and 2 new bits. I have 6 bits. I again play the same game. Now if you see, there are 3 carries going to the next column, and so on and so forth. So what you have to convince yourself is that at no place is it the case that a full adder is adding 3 bits which have different weights. It's always adding 3 bits with the same weight, because whenever I feed a carry to the next stage, whenever a full adder generates a carry, that carry has a weight of 1 more. And each one of these full adder guarantees that the 3 inputs it is adding together, the in 1, in 2, and the carry in, they always have the same weight. And we kind of keep percolating this thing. So this really constitutes our multiplier at the end, and a bunch of AND gates and these full adders. And as you can see, it has a very regular structure to it. Okay, so in fact, multipliers kind of are laid out very nicely on silicon because they're just a very repetitive structure. Okay, each one of these cells, if you think about it, has an AND gate, has a full adder, and it's kind of working like that. So I would like you to study this thing because there are many different ways you can structure this addition, but ultimately I have a whole bunch of bits. Some bits have weight of 1, some bits have weight of 2, some bits have weight of 4, 8, so on and so forth, and I have to add them together. Okay, and the final sum kind of appears out here. How can you do division? I want to divide A by B. So let's say you were on a computer where there was no division operation, a programming language. We remove the division operation. How would you do division? So right shift gives us a division, divide by 2 or 4 or right, but let's say I want to divide by something arbitrary. Let's say I want to divide by 7. How would you do it? Give any ideas. I mean, they don't need to be super efficient or anything. I'm just looking for like how do you do division? Yeah, go ahead.
You do right shift by the component, powers of 2, and then subtract.
Doesn't work.
Doesn't?
No, think about it.
You just take your lines and like make them go like
No, don't think at this diagram. There's nothing with this diagram. I just am making a digression because we talked about multiplication. Sorry. Go ahead.
do like long division as something gross, like long division.
Yeah, so long division is pretty, I guess you said gross, right? I mean, I think we always hated it at scales, right? Long division is gross, sure. But that's a possibility. We are not going to talk about division, but I just am taking this digression. What other ways you can do division? How about repeated subtraction? Right? I mean, if I want to divide A by B, I keep subtracting B from A and keep a tally of how many times I'm doing, and until I get a negative number, right? I mean, it's an inefficient way, but can certainly work. So that's one approach. Another approach is maybe I don't have a full divisor, but maybe I can take 1 over x, and then if I can do that, then I can always multiply. So I can a times a divided by b is the same as a times 1 over b, and if I can find some way of doing 1 over b, I could do that. Anyone remembers Taylor series expansion from your math classes, right? That's another way of doing division, right? Because it reduces everything to products and sums, okay? Are there other mathematical operators which can help you there? Logarithms, anyone remembers those, right? So if I want to do a by b, then I take log of a, log of b, subtract them, take anti-log, and find some way of doing logarithms, right? So one could do that also. So there are many different ways one could approach division. Long division, which was suggested by him at the back, is gross as it may be, it actually can work out. Okay, you just kind of something like this, but just working in the reverse direction. Okay, so even though we all hated it, it is actually subtract, shift, subtract, shift. Okay, so it's a very regular operation. We're not going to talk about it. This division is more complicated, but just want to throw it out that a lot of processors do have a hardware divider. Okay, costly as it may be, being able to do a division in a single instruction is very valuable. Okay, so they kind of do that. Another thing I want to bring out is how do we represent real numbers? Okay, so thus far we only talked about integers. In fact, we talked about positive binary integers. We talked about 2's complement numbers and stuff like that. There are many other number representations out there. So one thing I want to mention also is that sometimes people are really fond of decimal numbers. They really want to maintain decimal digits. And what is done then is that there's a format called binary coded decimal which is used. And the idea in binary coded decimal is we represent each digit of my decimal number separately. How many bits would we need to represent a digit? 4, right? I have 10 digits, I need 4 bits. So I need 4 bits to represent each d, and then the value of the number is d times 10 to the power j, because now they're representing digits. And in fact, a very good kind of problems you should explore doing is how do you go back and forth between these two? If I give you a binary number, how do you go to a decimal number? a binary coded decimal number, and vice versa. So let's talk about it. Let's say I give you a binary coded decimal number. So the idea in binary coded decimal is that D is 4 bits and they carry different weights. So let's say, for example, I were to have the number 78, just hypothetically. So binary coded decimal is called BCD. So let's say I want to represent a number 78. So in binary coded decimal, that would be 0111 1000. Okay, so 0111 represents 7, 100 is representing 8. I ask you to convert it into binary base 2 number. How would you do that? So what is the value of this number? 011 plus 1, the 78 is 7 times 10 plus 8, right? So it's the same as 0111 times 10. Yeah, it's getting a little bit crazy, right? Plus 1000, right?
Yeah.
Okay. What is 0111 times 10? How would you do that? We talked about it previously. How can I multiply a number by 10?
Times 8.
Times 8 and plus times 2, right? So that would be 0111 3. Hang on a sec. Times 2 times 4, yeah, 3 plus 0111 1 plus okay, and just allow for extra bits because otherwise you'll lose precision. So and then you add them up. So that's how you can go from BCD to binary. What about binary to BCD? How would you do it? Now that's a lot more complicated, okay? Because to get my lower digit, I have to divide by 10, right? I need to find remainder if I were to divide by 10, okay? And that's a lot trickier operation. Now it turns out there are some cool circuits floating around which let you do that, but they tend to be messy, so not something that I would sort of go over in the lecture. But Google for conversion from binary to BCD and you will see what kind of things they are there. Next type number, binary fixed point. Okay, so the idea is now I want to go and start representing real numbers. So there are many different ways we see real numbers being written. Okay, I mean you all probably have used calculators at one time or the other. So one way of representing real numbers is as fraction, 2 over 3. Those kind of things. Another way of representing binary numbers is we write it down like 3.1415, right? Or scientific notation, we can write like instead of writing arbitrary fractional numbers, we kind of always write it as a number front multiplied by 10 to the power something or exponent something. There are many different ways we kind of see these things. Binary fixed point basically says that I'm going to represent. Okay. So binary, it's my former student visiting from New York. Okay, so the idea in fixed point is the following. We take our bits and we basically say that the decimal point, or rather the point dividing the integer and the fractional part, is located at a particular place. So let's take a number. So let's say I were to write 11001. Okay, in a standard binary notation, the weights are 16, 8, 4, 2, and 1, right? So those are the weights. Let's say instead I were to say that there's always a decimal point or whatever, the point dividing the integer and fractional part out here. So it's a 5-bit number, but there is the integer and fractional parts are divided out here. Then we would say the weights are 8, sorry, 4, 2, 1, 1 over 2, 1 over 4. So we just divide all the weights like this. Okay. So same bit pattern 1, 1, 0, 0, 1 when interpreted as an integer has the value 25, whereas in the bottom case it would have the value I messed up somewhere. Yeah, 1, 1, 0. Whereas in the bottom case it would have the value, so 1, 1, 0, that's 6 plus 1 over 4. So it's 6 and a fractional part of 1 over 4, which is 6.25. Okay, and you can see that the top one is 25, and the bottom one is 6.25. 6.25 times 4 is 25. So this shifting this decimal point, I'll keep calling it decimal point, although that kind of doesn't really make sense. It's an integer fraction separator, where it goes really kind of essentially divides the number. If I move it to the left, I divide the number by 2. If I move it to the right, I divide the number by multiply the number by 2. So all that is happening out here is that my binary fixed point, you see the weights, they are going from minus m to plus n minus 1. Okay, so we give fractional weights to the bits which are to the right of the point, whereas integer weights 1, 2, 4, 8 to the left. So that's binary fixed point. The nice thing out here is that binary fixed point is kind of like integers. All that we're taking the same thing and we're just saying, imagine the separator was here, and that separator basically gives the whole thing a weight and kind of changes the weight by a certain amount. So in this case, since we put the separator after 2 bits, so as a result of this weight, everything got divided by 4. Okay, so it's just in our heads really. I can use the same adder, multiplier and all as long as I keep track of what the weights are, right? So I can just think of my number as 11001 and keep track that the whole thing has to be multiplied by or divided by 4 to interpret it like this. So 25 plus 25 is 50. 50 divided by 4 is 12.5. 6.25 times 2 is 12.5. So kind of this same thing, whichever way we approach it. Multiplication, same story. When I multiply two numbers, their weights are going to multiply too. Okay, so 6.25 times 6.25 is the same as 25 divided by 4 multiplied by 25 divided by 4, which is the same as 25 times 25 divided by 16. So when I'm multiplying, the weights multiply. When I add, the weights have to match up. So binary fixed point is really cool that I can just use my regular integer arithmetic and just kind of keep track of the weights. And so it is used in computers which do not have really real numbers. They only give you integer arithmetic, but through fakery of programming language, I can attach these weights and kind of deal with it. And then comes the real numbers. Okay, so the so-called floating point numbers. Okay, and these are your float and double in your programming languages, and these are actually represented differently in hardware, differently in computers. So how are they done? So these are just examples. Okay, so the idea behind floating point is the following. In floating point, this is the so-called scientific notation. I have a part which is called exponent and a part which is called mantissa. Mantissa, so a number is kind of like mantissa times 2 to the power exponent, and then there is a sign bit out here, much like in scientific notation on your calculators where we write 7.2 E3. That stands for 7.2 times 10 to the power 3. In this case, we are dealing with binary, so it is mantissa times 2 to the power E. And then there has to be a sign one. Okay, and this is represented specially. In fact, you need special adders and multipliers to represent these things. Our good old adder is not going to work. Since crazy things happen with these floating points, there is actually a standard way of representing them, IEEE 754 floating point representation, as it is called. It defines very clearly how many bits you need for exponent, how many bits you need for mantissa. So like, for example, if I'm packing everything into 32 bits, then 1 bit is reserved for sign, 8 bit is reserved for exponent, and 23 bits is reserved for mantissa. And moreover, the number's value is then 1 plus m. So the mantissa is viewed as a fraction between 0 and 1. Looking at this, imagine that mantissa can at most be 1. What's the largest floating point number I can represent? Most positive floating point number in IEEE 754. So my exponent is 8 bits. Exponent is going to have, so let's say exponent is always positive. So 8 bits of exponent can be up to 256. So the largest number is going to be 2 to the power 256 times some stuff. 2 to the power 256. How big is that?
What about the bias?
Huh? Yeah, I'll have to introduce a bias. Okay, yeah, so I have that. So that is to capture the sign. Okay, so it half will be negative, half will be positive. Okay, so it would be 2 to the power 128. 2 to the power 128. How much is it in 10 to the power something?
Yeah, I thought the bias was for negative powers.
Bias is for negative powers? No, the bias just shifts everything by that, so that you end up having a negative thing. So like you can represent negative, you can have negative powers also. So you can go to, you can go deep into fractional numbers also. Ignoring the bias part for the moment, let's look at the first part. Okay, so 2 to the power 128. Just get a sense. How big is it in power of 10? So how big is how many bits it takes to make 1,000? So 1,000 is 10 to the power 3, which is the same as 2 to the power roughly what? 9, right? 2 to the power 9, 2 to the power, sorry, 2 to the 10, you're right. So 2 to the power 10, so every 10 bits correspond to 1,000. So I have 128, so they have 13 groups of 10, so that roughly translates into power of 39. So that means I can represent numbers up to 10 to the power 40 or so, okay, roughly, okay. So that's floating point. There is something also called double, which actually uses 64 bits, and I think some modern things also go all the way up to 128. Okay, so there are more and more bits you can use. Again, we are not talking about it. These are pretty advanced topics. There's a course on computer arithmetic in the CS department which goes into these kind of things. Okay, let's say you want to represent temperatures from 0 to 100 in 0.1 centigrade. How are we doing? 53. Oh, I'm sorry. So we're going to pick this time up. But basically, we are done with this module. The remaining slides are just gratuitous. We are going to start on a new topic on Wednesday, and we'll have a midterm review session on Friday evening.